Imagine standing in space and watching a star disappear, not because something blocked it, but because its light was bent around an invisible monster. A black hole does not simply swallow light. It changes the very shape of space itself. Light isn't choosing to turn. It is following what has become the straightest possible path through a warped universe. That idea sounds impossible because we think of empty space as nothing, a stage where the universe performs. But according to Einstein, space is not a passive background. It stretches, it curves, it twists under the weight of matter. A black hole is where that effect becomes almost unimaginably extreme. It packs the mass of a star, or millions, or even billions of stars, into a tiny region. The result is a gravitational field so powerful that even light, the fastest thing in existence, cannot escape once it crosses a certain boundary. The strange part is that light doesn't suddenly become weak. It never slows in its own local space. Instead, the road beneath it has been bent into a new shape. Understanding that single idea changes how you see the entire universe. Most people picture gravity as an invisible force pulling objects together, like a giant cosmic magnet. That picture works well enough on Earth. Drop a ball, and gravity pulls it downward. But light has no mass, so why would gravity affect it? That question puzzled scientists for centuries. If gravity only pulled on mass, then light should fly perfectly straight forever. Yet the universe kept hinting that something stranger was happening. The answer is both simpler and more astonishing. Gravity is not pulling light sideways through space. Gravity changes space itself. Light simply follows the geometry. Think of driving on a perfectly straight highway. Now, imagine that highway quietly curves around a mountain. From inside the car, you never turn the steering wheel much. You simply stay on the road. Light behaves the same way. It follows the curved road that space has become. That realization transformed physics. It revealed that black holes are not cosmic vacuum cleaners. They are places where the geometry of reality becomes so distorted that even the paths of light are redirected. In 1915, Albert Einstein introduced general relativity. It was one of the most successful scientific theories ever created. 4 years later, in 1919, British astronomer Arthur Eddington traveled to the island of Principe during a total solar eclipse. The goal was simple, but incredibly difficult. Measure whether starlight passing near the sun appeared slightly out of place. Einstein predicted that the stars would shift by only about 1.75 arcseconds. That is roughly the apparent width of a coin seen from several kilometers away. When the photographs were analyzed, the stars had moved almost exactly as Einstein predicted. Imagine placing a marble on a stretched rubber sheet. The sheet bends. Now roll another marble nearby. It curves, not because anything grabbed it, but because the surface beneath it changed. Space behaves something like that. The rubber sheet analogy is imperfect because real space curves in 3 dimensions, not 2. But it captures the essential idea. That eclipse changed science forever. It showed that gravity could bend light itself. Once scientists realized gravity bends light, they discovered something extraordinary. massive galaxies can act like enormous cosmic lenses. In 1979, astronomers discovered the twin quasar. It looked like two identical quasars sitting close together. In reality, it was one incredibly distant object whose light had been split into two separate paths by an intervening galaxy. Some gravitational lenses produce complete circles called Einstein rings. Others create four identical images arranged like points on a compass. Some of these natural lenses magnify galaxies more than 10 billion light-years away. Without them, many of the earliest galaxies would remain invisible, even to our most powerful telescopes. Gravity becomes a telescope built by the universe itself. Near a black hole, the bending becomes almost unbelievable. If light passes close enough, it does not merely curve, it can orbit. But black holes isn't actually black. The name originates from an illusion that makes them blend perfectly into the black background of the surrounding universe. Black holes are concentrations of mass with a gravitational field so strong that light cannot escape once it crosses a certain boundary. That boundary is called the event horizon, and because no light comes back out from inside it, the black hole appears black. Close to the event horizon, the particles that make up light, called photons, stop traveling in straight lines. Out here, far from any mass, a photon flies straight, forever. Near a black hole, space is curved so severely that the straight line bends into a circle at about 1.5 times the radius of the event horizon. Lies a region called the photon sphere. A photon that enters it doesn't fly past. It orbits, around and around, circling a black hole it never touches. And the balance is impossibly delicate. Drift a fraction outward, and the photon escapes, carrying an image of a place no one can see. Drift a fraction inward, and it spirals across the horizon and is gone forever. In 2019, the Event Horizon Telescope revealed the first image of a black hole. The bright ring was not the event horizon itself. It was light. Light that had been bent into loops around the black hole before reaching Earth after traveling about 55 million light-years from galaxy M87. The darkness in the center was not simply an object blocking our view. It was a shadow cast by gravity itself. Black holes do more than bend space. They also distort time. General relativity predicts that clocks near stronger gravity tick more slowly than clocks farther away. This effect is tiny on Earth, but enormous near a black hole. In EJU-TLO, the Gravity Probe A experiment measured gravitational time dilation using a hydrogen maser clock launched aboard a rocket. The results matched Einstein's predictions with remarkable precision. As light climbs away from intense gravity, it loses energy. Its wavelength stretches. It becomes redder. Astronomers call this gravitational redshift. The light itself tells us how deeply it has climbed out of gravity's well. Many people believe black holes are giant cosmic vacuum cleaners. They are not. Replace our sun with a black hole of exactly the same mass, ignoring every practical consequence, and Earth would continue orbiting almost exactly as before. The orbit depends on mass, not on whether that mass is a star or a black hole. The real mystery lies elsewhere. What happens to information that falls inside? Quantum mechanics says information cannot simply disappear. General relativity predicts that anything crossing the event horizon cannot return. Those two ideas seem incompatible. Stephen Hawking spent decades studying this paradox. Today, physicists still debate whether information escapes in subtle quantum ways, remains encoded on the event horizon, or requires an entirely new theory of gravity. The greatest mystery is no longer whether black holes bend light. It is whether they bend our understanding of reality itself.